Okay, good afternoon. Hi everybody. I'm Marlos here. I work at Smin. I'm Aoml. So what I want to talk today is about the Antarctic Intermediate Water. I put the past, present, and future kind of holistic view, but apart from that, I'm still learning a lot, and hopefully I'll get some feedback from you, and hopefully future collaboration. So I'm going to present here two works. One is from 2012, so a little bit over a year ago, was published in Oceanography, and the other one was recently submitted to JGR. So for the first one, I'll just go quickly just to give the main idea of what the work was about, and focus more on the second one, that is more recent. So I want to thank my collaborators from the University of São Paulo, and Tenicar and Rasmus, Lisa over there. Yeah, so that's. So just to give a little introduction, why to study the Antarctic Intermediate Water. So here is a view of the ocean traces, and here on the left side we have the carbon inventory. So this is from Sabine and 2010, and from Sabine 2004 as well. And what they state is that the highest inventories of CO2 in the ocean are found in the most and intermediate water level. So it's really important for especially in this region here, we see a lot in the Southern Ocean. A lot of carbon uptake is done in these levels. Of, is there a certain depth? No, this is integrated over depth, so it doesn't give how it's stratified. So when you call at all, they plot more. I think Silvia used this figure too. So this is from the A16, I think the Wolf's line, and so we can see that in the south here, the Antarctic Intermediate Water has this low salinity. It's formed in this region, and low salinity going and across the equator over to the northern hemisphere. And it's also related to high levels of oxygen. And here's more a view of carbon over depth. So this depends a lot, I believe, on the methods estimated, but we see a lot of carbon over those depths. And so some of the mechanisms to explain this. So we have the deep water going south, and we have here in the Southern Ocean, close to Antarctica, we have this the wetting in those regions, and this is related to outgassing of CO2. And then we have after that the formation of the mold and intermediate water. So intermediate water sometimes is thought as the deepest mold water. So they are formed close to the front in the Southern Ocean, the polar and subantarctic front. So changes in this pattern can have a strong impact on climate, on the uptake of the CO2 and release back to the atmosphere. So a little bit of the formation of Antarctic Intermediate Water. So this is a paper by Saleh et al. 2010. So this measures the components of the subduction of the waters in the Southern Ocean. So subduction is when the water crosses the base of the mixed layer into the main thermocline during the winter. And we see that here in the Southern Ocean we have the Aoml. Aoml is mostly in the Southern Ocean up, so it's positive in this map. So that's how you have the upwelling of deep water. And so these are the location of the fronts here. And we see that the lateral induction, that is simply the water crossing the bent isopycnus, and then it's not exactly vertical, but it's just against the isopycnus. And we see that there's a lot of formation here in the Atlantic and a lot in the Pacific. And it's a stronger component of the subduction of water. Even though in this paper, they don't find a lot here in the Eastern Pacific, and some of the folks across the street, Harting and Rainer find they state that they can find this. So this paper uses Argo velocities to estimate these contributions and relate to 1,500 meter depth. So they are referenced at 1,500 meter depth, which may cause a problem as well. So, and the formation here, the formation of water with respect to the outcropping density in the ocean, we see that there's a paper from 2008, and we see that here the blue curve for the 20th century and the red curve for the 21st century. So we see that the formation of especially more deep water, this is in the Atlantic Ocean, this tends to migrate to lower densities. So this may have an impact too on the mechanisms. So also how in the Atlantic, and I'll focus more on the Atlantic, how it's a very intricate way that the Antarctic Intermediate Water behaves. So we have the Malvinas Current and also contribution from the Aoml Current here in the eastern side, and it follows mostly the Bengala Current extension around 30 south, and it spreads over to the northern hemisphere. So on the best climates, some work by Funky, I don't know if I'm right, but what they say is that that there's a strong link between the water formation, the deep water formation in the North Atlantic with the Antarctic Intermediate Water formation, mostly in the Pacific. So we have a kind of a seesaw relationship, whereas one fills the gap of the other. So this may have so this is from proxy data, and this may have happened in past climates. So, and in 2006, there's some people from Minicar, they have this run as part of the PMIP2 project, in which they run the CCSM tree in these two settings, for the last glacial maximum at 21,000 years ago, and the mid-Holocene at 6,000 years ago. And here is how the AMOC, the meridional Bethanic circulation, behaves in those runs. So here in the LGM, so this is the present day in comparison to the mid-Holocene and the LGM. So we see that the present day Dencar model is about 21 drivers for the CSM3. And so not many changes happen in the mid-Holocene. I will explain a little bit more what they refer to this time. And you have a decrease in the Aoml during the last glacial maximum, and also a shortening of the Aoml. And this may have impacted on the other side in the intermediate water. So the idea of this work is try to estimate the formation of this intermediate water in the Southern Ocean for this climate, and see if we can see some changes from the related to the North Atlantic deep water. So here, the introduction. So the last glacial maximum is a period of is the coldest time of the recent glacial period, and the temperatures were about 3 to 5 Celsius lower than is today. And at that time, there was a lowering of the sea level of up to 120 meters. And it impacts a lot the ice formation in the glacial region. So in the mid-Holocene is because we're changing in the precession of the Earth. So there's a change in seasonality due to that. And I'm not going to focus too much on this one because this, at least in the model, is very similar as we saw to the present day. So the surface prop, just so quickly, the surface prop, the surface salinity and the surface temperature for LGM. So these are anomalies with respect to the present day and in the mid-Holocene. So we see that LGM has a strong salinity anomaly over the globe, and it's much colder too. And we see like a stronger ACC in that time, and a shift here in the Gulf Stream, where it's located anomaly here. And in the mid-Holocene, there's more spread around the globe with a more patchy pattern. So the wind stress difference between these two time periods, for just LGM now, I focus more LGM minus PI. So mid-Holocene, the changes are really small, at least in the morning. So we can see that there's a shift here. So this the black one is in the LGM. So there's a shift south of the zero in stress curve, and the strengthening here of the westerly, and also strengthening the westerly in the southern hemisphere, without much changing in the location of the wind stress curve. So this may explain, for example, a stronger ACC here and the shift south of the Gulf Stream. And a little bit on the salinity difference with respect to the pre-industrial climate. So this is on the top is the salinity for the pre-industrial in the Atlantic and the Indo-Pacific both together. So we see the formation of the Antarctic Intermediate Water in the south, the North Atlantic deep water going north, and in the Pacific we have a formation of the intermediate water on both sides of the Pacific. And here you can see the difference between the LGM and the PI in the pre-industrial climate. Here the pattern is all positive, so it's all positive, and so we have a strong salinity anomaly in the Antarctic bottom water. With it fills most of the bottom of the ocean, so we have so the ocean is much more stratified, and we have a strong reduction here of the North Atlantic deep water in both basins. Yeah, yeah, and this, and then in the mid-Holocene, things are more over the, things happen more over the tropics, due to shifting the ITCD. And the temperature is the same pattern, so we see for industrial climate, cold temperature following the Antarctic bottom water in both basins, and we have a much colder temperature here in the LGM. So just take a look quickly at the TS relationship. So we plot the TS relationship to try to get the range of the intermediate water and estimate the formation patterns. So we see that here in blue is the LGM. In the North Atlantic deep water here, and the glacial time, the LGM, we have this pattern with some paper called the glacial North Atlantic intermediate water as a replacing part of the North Atlantic deep water. And then in all the basins you have ice. Antarctic bottom water for the LGM, filling most of the bottom of the ocean. So from this TS relationship, we get a range, for example, the salinity minimum, and then we estimate the densities in which they fill the ocean, and then estimate the water mass formation. So we use like the subduction. We use the subduction estimates of according to the kinematic approach, in which you have the lateral induction here, and here is the vertical transport over the main thermocline, the winter thermocline. And you see here so we calculate this for all the basins and see how changes in the water mass formation occur, especially during the LGM and the pre-industrial, which the pre-industrial is the black one and the LGM is in the blue. So for the mid-Holocene, you see that follows really close the black curve, so not much changes during that time. But we see here in the LGM, first we have the water forming in much denser range of the sigma of the density, and we have here a formation of in the North Atlantic. We have a formation of the North Atlantic intermediate water. And we have an increase in the formation in the intermediate level where the blue patches here. We have an increase in almost all the basins. In comparison to the PI, so this is the formation. And in the LGM, so we see an increase in mostly all the location of the intermediate water here, according to the reference of sigma that we found from the TS relationship. And especially in the South Pacific here, where we have from 29 values, we go up to 43 values. So this is a way to prove the thing that the hypothesis, the new hypothesis that is there an increase in the Antarctic Intermediate Water at those times where the North Atlantic deep water was smaller, and we can say yes, but some of the changes are of course associated with a stronger band of westerlies in the south, and we also have the North Atlantic Intermediate Water as part of this replacement, not only in the south and in the Pacific, but in the whole Southern Ocean. And we also have a stronger formation of Antarctic bottom water, and it is known to be this feature that traps the CO2 in the bottom, and then the CO2 can come back to the surface, and is one of the ideas that the whole CO2 was trapped in the bottom of the ocean, so we have a much cooler climate due to this more stratified ocean. Yeah. So I go to more recent, more contemporaneous changes now. So I want to talk about historical changes over our historical record here. So this is a paper by Smin and Johnson, 2011. So they estimate the trends in the southern hemisphere of over the Antarctic Intermediate Water level. So for pressure, temperature, salinity, and density. And we see that in most of the oceans, there's an increasing temperature over the intermediate level. And in the South Atlantic here, we have a strong anomaly, a stronger increase of salinity in that region, which both together create a lower density in that region. So the idea is to try to investigate what would be the causes of that. So in Schmidt and Johnson, they say, two of the players, strong players, would be the South Atlantic mode trends over the Southern Ocean, and also the SST changes. So we use for this work two different models. One is the SODA 2.26. So this version of the SODA is a top model with a 1/4 degree horizontal resolution, 40 vertical levels in a monthly phase. It uses the 20th century analysis as a forcing and only assimilates SST, doesn't assimilate hydrography, just SST from the ICOAD 2.5, which is just in situ measurement. There is no satellite. So this product is used to validate satellite SST. So it's just from the historical temperature record. And also use the University of Victoria climate Earth system couple model. The last version, the 2.9, which is a low resolution model. The 1.8 and 2.6 resolution uses the MOM2 as the ocean component. And so I'm going to explain a little bit the experiment a little bit later in the second part of this. So first, analyzing the SODA, just a quick comparison with the Argo. So this is the Argo from the IPRC climatology. Show how it behaves over this is around the 25 west. So this is close to the A16 line, the Wolf's line. So for SODA, we see that has a lower salinity tone, and is more fatty here. It's much noisier here. So this is for the 2000 average. But the patterns look similar. And the SODA, it generally goes deeper up to 1,200 meters, while Argo just goes to 1,000 meters. The have this strong change here due to the depth of the intermediate water. So this is the salinity minimum over the Atlantic. So we see that this is from 33.6 to 34.6. And we see similarities. So, but soda is a little more saltier, and there's a stronger front here due to the stronger descent of the isopycnus in that region.
Aoml here are already in the Decadal.
No, this just assimilate SST, the soda. But I want to analyze the trends over the last 50 years. If we include hydrography, which is highly based on the last decade, we see trends there are mostly due to the measurement coverage. Then, so SST is better over time to assimilate, and then we see more consistent dynamically. So in the South Atlantic at 25 west, so you see how the TS changes over the decades. So I started analyzing since the 60s, because in the 60s, the ICOAD is when they start over 2 million profiles. I believe a year, 2 million profiles. No, 2 million profiles a decade. Over those times until 2000. And we see that at 35 south, we see all the patterns, we see mostly increase of salinity in all locations. In the 2000s, the green one. So increase of salinity. This is in agreement with some other works that says that there's an increase in the hydrological cycle in the ocean. And at central and most water depths here, we see on isopycnal levels, we see a decrease in salinity here in comparison to the other locations. Of course, in 20 south, these changes are not very prominent as they are in the other locations. But they mostly follow a pattern that in south to in 30 south. So we have a decrease in salinity here and an increase in salinity at the intermediate level. So this is a zoom here at the intermediate water, so there's an increase in salinity in that region. So this is in agreement with Schmidt and Johnson for intermediate level. So to see how significant they are over time. So these are I created here some indices for the salinity minimum in the ocean. So we get the salinity at the location of the salinity minimum, and get the salinity, sigma density, and temperature. So I plot here the three standard deviations just to give an idea of how significant trends are over time. And you see that at 30 south, we see that we have over the late 90s and 2000s, we see that the trend starts back in this level. And we see actually no other locations at 35 south too, that after 2000, all the changes are significant, whereas over other periods, not all of them are significant, but we can see also some variability over time. So so for the two regions, we see an increase of salinity, an increase of temperature, and a decrease of density, in agreement again with symmetrical in Johnson. So this is just to show how the density are related to salinity and temperature at different locations in the South Atlantic. So here for 30 south. So this is the what I call thermal and hollow peak no contribution for density. So we keep for the salinity contribution, we keep the temperature as the mean, and let the salinity evolve over time, and then we see just the contribution of salinity, and the same for the temperature, and here's the total density. And we see that at 30 south, the density, which is the total density, which is the red one, follows really closely the